Aldehydes and ketones are organic compounds that contain carbon-oxygen double bonds. That is, the carbonyl group as a functional group. They have the general molecular formula CnH2nO. Aldehydes and ketones closely resemble each other in most of their chemical properties. Hence, they are often collectively referred to as carbonyl compounds. However, aldehydes and ketones differ in the nature of the groups that are attached to the carbonyl group. In aldehydes, one of the two available valencies of the carbonyl group carbon is essentially satisfied by an H atom, and the other by a hydrogen atom, an alkyl group or an aryl group. Hence, the general formula for aldehydes is RC double bond OH. If R is H, then the corresponding aldehyde is formaldehyde. If R is the methyl group, then it is an acetaldehyde. And if R is the phenyl group, then it is a benzaldehyde. In ketones, the two valencies of the carbonyl group are satisfied by two alkyl or aryl groups, R and R', which may be the same or different. If R and R' both represent the same group, then the ketone is called a simple ketone. If R and R' are different, then the ketone is called a mixed ketone. The general formula for ketones is RC double bond OR'. For example, acetone represents a simple ketone where both R and R' are the same. That is, CH3. Benzophenone, where both R and R' are C6H5, also represents a simple ketone. On the other hand, acetophenone, where R is a methyl group and R' is a phenyl group, represents a mixed ketone. Due to this difference in the nature of the groups attached to the carbonyl group, in aldehydes and ketones, their reactivity is different. For example, aldehydes oxidize with ease as compared to ketones. Let us now look at the significance of these compounds. Aldehydes and ketones are well known for their fragrance and flavor. For example, the smell of acetaldehyde is reminiscent of apples. Also, vanillin from vanilla beans, salicylaldehyde from meadows sweet, and cinnamaldehyde from cinnamon have very pleasant fragrances. Aldehydes and ketones both find significance in several biochemical processes. For example, glucose, a polyhydroxyaldehyde, is the chief product in photosynthesis. Respiration, which takes place via the combustion of glucose, is associated with the liberation of energy. Thus, it is the ultimate source of energy in plants and animals. These compounds have considerable industrial significance. They are used as solvents and as starting material for the synthesis of several other products. For example, acetone and ethyl methyl ketone are common industrial solvents. Formaldehyde is used to prepare bakelite. Urea formaldehyde glues and other polymeric products. Acetaldehyde is chiefly used as starting material for the synthesis of acetic acid. Ethyl acetate, drugs, and polymers. Benzaldehyde is used in the perfume and dye industries. Certain compounds are used for preparing adhesives, paints, resins, plastics, fabrics, and so on. Like other organic compounds, aldehydes and ketones also have two systems of nomenclature. They are the common system and the IUPAC system. The common names of aldehydes are derived from the names of the corresponding carboxylic acids that they form on oxidation. They are named by replacing the IC acid of carboxylic acid by aldehyde. Thus, the aldehydes formaldehyde, acetaldehyde, and benzaldehyde are named after formic acid, acetic acid, and benzoic acid respectively. As you can see, they are named by replacing the suffix IC acid with aldehyde. The positions of the side chains or substituents in the carbon chain of aldehydes are indicated by the Greek letters alpha, beta, gamma, and delta. The carbon that is directly linked to the aldehyde group is alpha carbon. The next carbon is beta carbon, and so on. For example, the given compounds can be named alpha-hydroxybutyl aldehyde and beta-bromobutyl aldehyde respectively. In the IUPAC system, aldehydes are named by replacing the E of the corresponding alkane by Al. Hence, the IUPAC name for aldehydes is alkanal. For example, the IUPAC name for formaldehyde can be written by replacing the letter E of the corresponding alkane methane by Al. Hence, the IUPAC name for formaldehyde is methanal. Similarly, the IUPAC names for acetaldehyde, propionaldehyde, N-butyraldehyde, isobutyraldehyde, and valeraldehyde are ethanal, propanal, butanal, 2-methyl-propanal, and pentanal respectively. The substituents in the aldehydes are prefixed in alphabetical order along with numerals indicating their positions in the carbon chains. Thus, the IUPAC name of the given compound can be written as 3-bromo-2-chloro-4-methyl-hexanal. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehyde group. Thus, the given compound is named 2-ethyl-3-methyl-pentanal. It must be noted that the C2 of the IUPAC name corresponds to the alpha of the common name. For example, the compound shown here bears the IUPAC name of 2-methyl-pentanal, while its common name is alpha-methyl-valeraldehyde. Here is a list of some aldehydes with their common and IUPAC names. From the list, you can see that the IUPAC name for alpha-chloroacetaldehyde is 2-chloroethanal and for acrolein it is propanol. In the IUPAC system, when the aldehyde group is attached to the ring, the suffix carbaldehyde is added after the name of the cycloalkane. For example, in cyclohexanaldehyde, the aldehyde group is attached to a 6-member cyclohexane ring. Hence, its IUPAC name can be written by adding the suffix carbaldehyde to the cyclohexane. That is, cyclohexane carbonaldehyde. Similarly, the IUPAC name for benzaldehyde can be written as benzene carbaldehyde. Note that the common name benzaldehyde is also accepted by IUPAC. To indicate the substituent on the ring, the numbering of the ring starts from the carbon atom to which the aldehyde group is attached. For example, the IUPAC name for gamma-methyl cyclohexanaldehyde is 3-methyl cyclohexane carbaldehyde. Similarly, while writing the IUPAC name for orthohydroxybenzaldehyde or salicylaldehyde, the substituent hydroxyl group gets the second position as the numbering of the ring starts from the carbon atom attached to the aldehyde group. Thus, the IUPAC name for this molecule is 2-hydroxybenzene carbaldehyde. Now let's look at the common names and the IUPAC names of some compounds. The common name, metachlorobenzaldehyde, is written as 3-chlorobenzene carbaldehyde in the IUPAC system. Similarly, para-nitrobenzaldehyde is 4-nitrobenzene carbaldehyde. Phthalaldehyde is benzene 1,2-dicarbaldehyde. Vanillin is 4-hydroxy 3-methoxybenzene carbaldehyde. Crotonaldehyde is 2-butanal and cinnamaldehyde is 3-phenyl propanol. Let us now turn our focus to the nomenclature of ketones. In the common system, ketones are named simply by adding the suffix ketone to the name of the two alkyl groups. In case of simple ketones, where both the alkyl groups are the same, the prefix di is used for the alkyl group. For example, the compound CH3 C-double-bond-O, CH3, is named dimethyl ketone or simply acetone, while C2H5 C-double-bond-O, C2H5 is named diethyl ketone. In case of mixed ketones, the two different alkyl groups R and R' are mentioned in alphabetical order. For example, the compound CH3 C-double-bond-OC2H5 is named ethyl-methyl ketone. Similarly, CH3 C-double-bond-OC3H7 is named methyl N-propyl ketone. The positions of substituents in ketones are indicated by the Greek letters alpha, alpha dash, and beta, beta dash, and so on, where alpha, alpha dash are given to the carbon atoms adjacent to the keto group. For example, in the given molecule, the substituents, 2 bromine atoms, are present on the alpha dash and beta carbons. Hence, it is named alpha dash beta dibromodiethyl ketone. Alkyl phenyl ketones are usually named by adding the acyl group as a prefix to phenone. For example, when CH3 C-double-bond-O is attached to benzene ring, it is named acetophenone. Similarly, the molecule C2H5, C double bond O, C6H5 is named propiophenone. The ketone in which a carbonyl group is attached to two benzene rings is named benzophenone. According to the IUPAC system, ketones are named by replacing the E of the corresponding alkane with -one. The longest chain carrying the carbonyl group is considered the parent chain, and the numbering begins from the end nearer to the carbonyl group. The compound shown here is named 4-methyl-hexane 3,1. In certain polyfunctional compounds, if the carbonyl functional group of the ketone is present as a substituent, then it can be indicated by the prefix oxo, and a number is indicated to show its position in a molecule. The example here contains three functional groups: hydroxyl, aldehyde, and ketone. According to IUPAC rules, as the order of preference while naming is aldehyde, ketone, and then hydroxy, the carbonyl functional group of the ketone and the hydroxyl group of the alcohol are treated as substituents. Hence, the IUPAC name is 5-hydroxy-4-oxohexanal. As aldehydes and ketones contain the same carbonyl group, their properties and methods of preparation are quite similar. Methods for the preparation of aldehydes and ketones include oxidation of alcohols, dehydrogenation of alcohols, ozonolysis of alkenes, hydration of alkynes, reduction of acid chlorides, and reduction of nitriles. Let us learn about each one of these in detail. Let us begin our discussion with the preparation of carbonyl compounds from alcohols. You have already learned that primary and secondary alcohols yield aldehydes and ketones on oxidation. The process of oxidation of alcohols involves the loss of alpha hydrogen. That is, the hydrogen atom attached to the carbon bearing the OH group. In the presence of reagents such as pyridium chlorochromate, PCC, or acidified potassium dichromate, or acidified potassium permanganate. Now, since primary alcohols contain two alpha hydrogens, they can either lose one of them to form an aldehyde selectively in the presence of pyridium chlorochromate, PCC, or can lose both of them to form a carboxylic acid in the presence of acidified potassium permanganate. The conversion of a primary alcohol into an aldehyde is difficult because aldehydes are susceptible to further oxidation. One of the best reagents for the conversion of primary alcohols into aldehydes is PCC. Note that the oxidation of primary alcohol to carboxylic acids is usually accomplished by the use of acidified potassium permanganate. For example, ethanol on oxidation with PCC gives ethanal, but gives ethanoic acid in the presence of acidified potassium permanganate. On the other hand, a secondary alcohol loses its only one alpha hydrogen to form a ketone in the presence of acidified potassium dichromate. For example, isopropyl alcohol on oxidation in the presence of acidified potassium dichromate gives propanone or acetone. Another method of preparing carbonyl compounds from alcohols is by the dehydrogenation of alcohols. This method is suitable for the oxidation of volatile alcohols. It involves passing vapors of an alcohol over metal catalysts like silver or copper. Dehydrogenation of primary alcohols yields aldehydes, while that of secondary alcohols yields ketones. For example, when vapors of ethyl alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and ethanol is formed. However, isopropyl alcohol yields acetone on dehydrogenation. Carbonyl compounds can also be prepared from the ozonolysis of alkenes. Ozonolysis involves the cleavage of the double bond by the addition of ozone to give a cyclic product called ozonide, followed by hydrolysis in the presence of zinc dust. Depending upon the substitution pattern of alkenes, ozonolysis yields either aldehydes or ketones or both. For example, 2-butene yields 2 molecules of acetaldehyde on ozonolysis, while 2,3-dimethyl-but2-ene yields 2 molecules of acetone. A molecule such as 2-methyl-2-butene yields a mixture of acetaldehyde and acetone on ozonolysis. Hydration of alkynes is yet another method for the preparation of carbonyl compounds. This method involves the addition of water to alkynes in the presence of mercuric sulfate and sulfuric acid to form aldehydes or ketones as the final product. For example, acetylene on hydration gives unstable vinyl alcohol, which tautomerizes to form the acetaldehyde. All other alkynes yield ketones in similar manner. For example, propyne gives acetone on hydration. Carbonyl compounds can also be prepared by the reduction of acid chlorides. Aldehydes can be prepared by the reduction of acid chlorides with hydrogen in the presence of palladium on barium sulfate in quinoline. This reaction is called Rosenmund's reduction. Aliphatic and aromatic aldehydes can be prepared by this method. Note that ketones cannot be prepared by this method. For example, adding hydrogen to acetyl chloride in the presence of palladium on barium sulfate in quinoline yields acetaldehyde. Similarly, Rosenmund's reduction of benzoyl chloride gives benzaldehyde. Ketones, on the other hand, are prepared by the treatment of acid chlorides with dialkyl cadmium. Dialkyl cadmium can be prepared by the reaction of cadmium chloride with Grignard reagents. For example, the reaction of methyl magnesium bromide with cadmium chloride gives dimethyl cadmium. The treatment of dimethyl cadmium with propanoyl chloride gives ethyl methyl ketone. Aldehydes and ketones can both be prepared from nitriles. Let's see how. Aldehydes can be prepared by the reduction of nitriles to imines followed by hydrolysis. The reduction of a nitrile to the corresponding imine by stannous chloride in the presence of hydrochloric acid, followed by hydrolysis to yield the corresponding aldehyde, is known as the Stephan reaction. For example, ethane nitrile on reduction in the presence of SnCl2 and HCl gives ethynylamine. This on hydrolysis in the presence of an acid gives ethanol as the final product. Alternatively, selective reduction by diisobutyl aluminium hydride (DIBALH) two imines followed by hydrolysis also yield aldehydes. For example, ethane nitrile, on reduction in the presence of DIBALH followed by hydrolysis, yields ethanal. Similarly, DIBALH can also be used to reduce esters to aldehydes, as shown here. Ketones, on the other hand, can be prepared by treating a nitrile with the Grignard reagent followed by hydrolysis. For example, propiophenone can be prepared by treating propane nitrile with phenyl magnesium bromide in ether followed by hydrolysis. Let us now look at the preparation of aromatic aldehydes and ketones. Aromatic aldehydes can be prepared from benzene or aromatic acid chlorides or methylbenzene or from benzyl halides. Let us discuss each method. Aromatic aldehydes can be prepared by treating benzene or its derivatives with carbon monoxide and trihydrogen chloride gas in the presence of anhydrous aluminium chloride or cuprous chloride. This reaction is known as the Gattermann-Koch reaction. For example, benzaldehyde can be prepared by treating benzene with a mixture of carbon monoxide and dry HCl gas in the presence of anhydrous ElCl3. As you have seen earlier, Rosenmann's reduction of benzoyl chloride with hydrogen in the presence of palladium on barium sulfate in quinoline also gives benzaldehyde. Benzaldehyde or substituted benzaldehyde can also be prepared by the oxidation of methylbenzene with chromyl chloride to a chromium complex followed by hydrolysis. This reaction is known as the Etard reaction. Benzaldehyde can also be made from toluene. When toluene or substituted toluene is treated with chromic oxide in acetic anhydride, benzylidene diacetate is formed. This, on hydrolysis in the presence of an acid, yields the corresponding benzaldehyde. The hydrolysis of benzyl halides also yields aromatic aldehydes. For example, the hydrolysis of benzyl chloride, which is obtained by the side chain halogenation of toluene, gives benzaldehyde. Remember that this is the commercial method for manufacturing benzaldehyde. Aromatic ketones are more conveniently prepared by the Friedel-Crafts acylation. Benzene reacts with acid chloride in the presence of anhydrous aluminium chloride to give the corresponding ketone. This reaction is known as the Friedel-Crafts acylation. For example, benzene reacts with acetyl chloride and benzoyl chloride in the presence of anhydrous aluminium chloride to give acetophenone and benzophenone respectively. The physical and chemical properties of aldehydes and ketones are determined by the structure of the carbonyl group. It is, therefore, very important to understand its structure. Like the carbon-carbon double bond in alkenes, the carbon-oxygen double bond of the carbonyl group is composed of one sigma bond and one pi bond. The carbon atom in the carbonyl group undergoes sp2 hybridization in its excited state, leaving 1 out of 3 p orbitals unhybridized. The carbon to oxygen sigma bond is produced by the overlap of one sp2 orbital of carbon with a p orbital of oxygen. On the other hand, the carbon-to-oxygen pi bond is formed by the sideways overlap of the p orbitals of carbon and oxygen. The remaining two sp2 orbitals of carbon form two sigma bonds with the s orbital of hydrogen, as in formaldehyde, or one sigma bond with the s orbital of hydrogen and another sigma bond with an sp3 orbital of the carbon of the alkyl group, like in other aldehydes, or two sigma bonds with two sp3 orbitals of the carbon of the alkyl group, as in ketones. Thus, the carbonyl carbon and the three atoms attached to it lie in the same plane with a trigonal coplanar structure and a bond angle of 120 degrees, while the pi electron cloud lies perpendicular above and below the plane. It is important to note that the carbon-oxygen double bond in the carbonyl group is different from the carbon-carbon double bond in alkanes. In case of alkenes, the pi electron cloud is equally shared by two atoms, whereas in the carbonyl group, the pi electron cloud is attracted more towards the oxygen atom due to its greater electronegativity. Consequently, in the carbonyl group, the oxygen atom acquires a partial negative charge, while the carbon atom acquires a partial positive charge, thus making the carbonyl a polar group with a dipole moment value of 2.3 to 2.8 dBi units. However, the high value of the dipole moment can be accounted for both the inductive effect and the resonance effect. Now, let us look at the physical properties of carbonyl compounds. At room temperature, formaldehyde is a gas and acetaldehyde is a volatile liquid. Other aldehydes and ketones are liquids or solids at room temperature. Aldehydes and ketones have higher boiling points than hydrocarbons and ethers of comparable molecular weights. This is due to the weak intermolecular dipole-dipole interactions. Observe this table about compounds of almost similar molecular weights, 72 to 74. We see that non-polar hydrocarbons, like N-pentane and weakly polar diethyl ether, have lower boiling points than that of polar N-butyraldehyde and ethyl-methyl ketone. However, their boiling points are lower than that of N-butyl alcohol and propionic acid. This is because carbonyl compounds are not capable of forming intermolecular hydrogen bonding by themselves, since they contain a hydrogen bonded to carbon, but not to oxygen. Aldehydes and ketones are soluble in the usual organic solvents like benzene, ether, and chloroform. To know their solubility in water, refer to this table, which shows the solubility of a compound in grams per 100 grams of water. We see that the lower aldehydes and ketones, such as formaldehyde, acetaldehyde, and acetone, because of their ability to form hydrogen bonding with water, are miscible in water in all proportions. Notice that solubility decreases with an increase in the length of the carbon chain. The lower aldehydes and ketones have a characteristic pungent odor. With an increase in the size of the molecule, the odor becomes less pungent and more fragrant. Therefore, many naturally occurring aldehydes, such as vanillin from vanilla beans and cinnamaldehyde from cinnamon, and ketones such as acetophenone, are used to blend perfumes and as a flavoring agent.